Hello, how's it going? So far, you'll notice that I've been very careful not to put the cube on the edge of the screen or behind the viewer. But that all changes today. We're going to have a look at clipping polygons. This will be quite a big session, but hopefully we'll have a really cool result which is very satisfying. Let's get into it. So in order to achieve this clipping, we're going to be using an algorithm called the Sutherland-Hodgman algorithm. It's a pretty good general algorithm. All we need is an edge table. That's a list of vertices which define the points, the endpoints of edges, and a set of some sort of boundaries. And then we work through the set of boundaries, clipping one at a time, and we get our result. We have the pseudocode down here on the Wikipedia article, and this is the code that I'll be using for this is the code that I'll be using, pretty much. So let's have a look at an example of this code in action. All right, so let's say that we have a screen area with 4 boundaries, and I'll make a polygon which is partially off screen. Like that. And I'm going to label these, I guess, point 0, 1, 2, and 3. So our edge table will contain the points 0, 1, 2, and 3. When we go to draw this, we would draw an edge from 0 to 1, an edge from 1 to 2, an edge from 2 to 3, and then an edge from 3 to 0. We'd wrap back around. So let's take this and let's consider what I'll call the x minus boundary, the left-hand boundary. So we'll have some sort of output from there. Okay, so what we'll do is we'll start with point A will be 0. Point B will be the next point in the table, which is 1. And point C, if we look at the x minus boundary, there's an intersection point here. I'll call this A. It doesn't matter what I call it. So I go through a loop here. I say, is point B inside the boundary? Well, yes. Point B is to the right of the x minus boundary, so it's inside. Okay. Is point A not inside? Well, here's the boundary. Here's point 0. That is outside of the boundary. Okay, so the algorithm says we need to add C. So we'll add the intersection point, and then we'll add B. So that is point 1. Okay. Then that's done. So we'll look at the next one. So now we're going between 1 and 2, and we don't really, we'd have some imaginary, if we followed this, traced this off to the left, we'd have some intersection point over here. But let's keep going. So is point B inside? Yes. Is point A not inside? No, point A is inside. So we won't add the intersection point, we'll just add point B, which was, sorry, I mixed that up. Point A was 1, point B was 2. Okay, then we look from 2 to 3. So 2 is point A, being very clear here. 3 is point B. Okay, is point B inside? Yes. Is point A not inside? No. Okay, so we don't add the intersection point. By the way, the intersection point here, if we trace this line along, would be somewhere here. We don't worry about that. So we just add point B, which is 3 here. And then we go from 3 to 0. We're wrapping around here. So we say, okay, is point B inside? Oh, by the way, we have an intersection point, which I'll just call it. I don't want to be confusing here, but I'm using letters for the intersection points. So point B in this case is 0. It is not inside. So we go down, we skip down. Okay, is point A inside? Yes, it is. So we'll add the intersection point. So now we've done that boundary, and just for brevity for this example, I'm going to skip the it doesn't matter what I call this. I'll call this the y plus. I'll skip the y plus and the x plus boundaries because they don't have any clipping. But when we implement this, we would have to include these. I'm just going to have a look at the y minus boundary. So if we look at the input table, it has to be the result of the previous clipping. So that is from the point A to the point 1, 2, 3, B, and then back around to A. Okay. So we'll keep going here. So now we'll go from point A to 1. Okay, so we say, is the end point inside? No, it is not. And by the way, just fill in the intersection points right now. Okay, so is the end point inside? No, it absolutely is not. Is the previous point inside? Yes, it was. Okay, so we'll add the, just thinking here. Yep, we'll add the intersection point, C, and then we'll go from 1 to 2. Okay, is 2 inside? Yes, it is. Is 1 not inside? Yeah, 1 is not inside, so we'll add the intersection point, D. Okay, then from 2 to 3, both of those are inside. So we have 3 is inside, 2 is, yeah, skip this. We'll just add, there we go. I got tricked. There's something we missed. Okay, so in the previous iteration, going from point 1 to 2, point 1 was not inside, so we add the intersection point, but then after that we add point B, so we add 2 in this case. Okay, excellent. Now we're going from 2 to 3, and yeah, 3 is inside, 2 is as well, so we skip this and we just add 3. And then from 3 to B, well, B is inside of this y minus boundary, and so is 3, so we skip that point and we just add B. Okay, there we go. So if we were to sketch these out, our clipped polygon, oh, yep, and then what am I missing? Then we go between B and A. Both of them are inside, so we just add A. Okay, so there we have it. So sketching this out, we go from C to D, that's one edge, and then we go from D to 2, that's the other edge, and then from 2 to 3, then 3 to B, then B to A, and then A back around to C. So there we have it, that's our clipped polygon. Now you might be saying, hey, what's the benefit of this? The benefit of this is that we are interpolating when we find the intersection point, and we're not just interpolating the position, okay? If we just had a simple clamp function here, that would work perfectly fine. But because we're interpolating everything, not just the position, we can send these vertices along with custom data structures. For instance, if we want to declare a color at each vertex, and then when we find the intersection point, we also interpolate the color between the 2 points. Or if we have texture coordinates, then we can interpolate the texture coordinates between the 2 points. So that is why this algorithm is really useful, and more useful than a simple min-max sort of thing. Anyway, so let's go ahead and start to implement this in code. All right, so here we are in the project. Like I said, this is going to take a few steps, a few stages, but how do we get there? Just one step at a time. So let's open up our linear algebras header, and we have all of these structs here. I'm going to define another struct, and that is the edge table. Now the edge table is right now just going to describe a bunch of points that we would need. So we'll just go so we're going to have an array of 4D vectors, which I'll just call vertices, and we'll need the vertex count so we can loop through properly, and I'm going to call this an edge table. Okay, cool. So now what I'll do is I'll just pop down below, and I'm being a little lazy here. Since I'm being lazy, I'll just define these functions here. Okay, so I'm going to have my clipping function. My clipping function needs to return an edge table. I'll call this clip. I'll stick with the convention. Linalg clip against boundary. Now we don't know what our boundaries are. We'll look at that later. Spoiler alert, they're planes. But what we'll do is we'll take an edge table as our input, and we'll have some sort of boundary. I know this is dodgy. I haven't finished this yet. So what we'll do is just head over to the source file. I'll just do this for now. Okay, so first thing we're going to need to do is create an edge table that we will return. And now what I'm going to do is I'm going to be a little bit dodgy, and that is I'll think about the worst case. So I'm getting in some sort of polygon. I don't know it. Well, it might have 4 edges, it might have more, it might have less. But I'll think in the worst case, this isn't even mathematically possible, but in the worst case, every edge could be clipped, and we could have a maximum of double the number of vertices. So what I'll do is I'll take output vertices, and I'll allocate some memory. So I'll go back 4. In the worst case. Now, you could argue that if we know how many planes we've got, and we have some reasonable estimate for how many vertices each of our polygons have, then we should have like a maximum of 16, and we could have a constant array, a constant size array of 16 or something. Let's just go with this for now. Okay, so we'll also set the vertex count. And then the idea is that we are consuming the input in order to produce the output. So we had better make sure that we're freeing the memory consumed by the input. So before we return everything, we'll free the input's vertices. And now we can start working. So what we'll do is we'll just loop through. Okay, and now we'll get an idea of what our points are. We'll build up our edges. So we'll have some vec4, which is point A. That will be the ith vertex. Okay, now, just a little note. I have had so many nightmares dealing with modular arithmetic in C++. Just keep it positive. Just for whatever reason, C++ hates negative modulus. Now, I tried setting this to unsigned integer. It still didn't work very well. So, yeah. And then what we'll do is we'll say vec for C equals just go with that for now. Okay, so we'll start off, we'll have our start point, our end point, and our midpoint. Then we'll follow along and we'll say, let me just do this for now. And I'll just write a comment. Okay, so this is okay, so this is just following through with the pseudocode that I was writing before, and we don't really know what our boundaries are yet. We don't really have intersection or visibility tests yet, so I'm just filling it in with comments. But what we do if B is visible but A is not visible is we put in the intersection point. So we say output vertices, and then no matter what we put in B because it is visible. And there we go. So if it's the case that B is not visible, but the point A is visible, well, remember that the point A was the point B from a previous iteration, so we don't need to add A again. What we'll do is we'll just add the midpoint. Yeah. Okay. So there we go. We have, that's the algorithm, pretty much. I guess let's just, right now, before we look at the planes and stuff, let's go back to our program and start setting this up a little bit more. So we'll just go back to control, to the header, and then that was the backface test. Let's make a clipping test. Okay, and then we'll go to our source file. And then down here, we'll run the clipping test. And yeah, the usual business. So I'll just grab all of this backface stuff. So I'm just looking here. Okay, so what I'm going to do is I'm going to build the projection, but I'm not going to apply it. So I'll just use the model transform here, and I won't do perspective division yet. Okay, but what I will do when I build the projection matrix, I'll just standardize a lot of this stuff. So I'll go float. Okay, and that will be useful later on. But anyway, so I get in here and I'm getting ready. I've done my backface culling. Let's pretend that's working for now. We will have to modify it a little bit. But before I go into draw, I'm going to need to build an edge table. Okay, so what this is doing is it's very simply just pulling out the vertices that we would draw for the plane and sticking them in the edge table ready to be drawn. The next thing I need to do is clip. So I'll say edges equals, actually, I changed my mind. Let's leave it at this point. Let's leave it at this point and start looking at the mathematical structures that we're going to use to clip. All right, so what's it all about? It's basically, we're going to use planes to describe the boundaries that we're going to clip against. Now, how do we make a plane? Well, a plane is a mathematical structure where every point on the plane, so if I put a general point P that has an X, Y, and Z coordinate, then some constant times X plus Y plus Z plus D equals 0. Fair enough. So how do we get this X, Y, this A, B, C, and D? Well, to create a plane, we'll have two sort of components. We'll have a point somewhere on the plane and a normal vector. Now, by definition, the direction vector from our point to a general point on the plane must be orthogonal with the normal, which means the dot product here must come out to 0. So then if we were to rewrite this, because the dot product is a linear operator, this splits out into P dot n minus P naught dot n. Comes out to 0. Now, P just has the coordinates x, y, z. So what this is really saying is normal x times x plus normal y times y plus normal z times z minus the dot product of the fixed point with the normal equals 0. And so we can see that the A, B, and C coefficients are the components of the normal, and we can sort of take this dot product and define negative that dot product as the component D. So yeah, there we have it. For a given normal and point, these are the expressions we can use to get the plane coefficients. Okay, so all well and good. The next thing I need to know is, when is a point in front or behind of a plane? So imagine we have some plane and we have the initial point which was used to define the plane and the normal vector. And then I want to consider 2 points. I'll call this point A and I'll call this point B. Now, clearly A is not behind the plane. It's in front of the plane. It's in the direction vector from P0 to A is within 90 degrees. It's on the same side as the normal. On the other hand, if we look at the direction vector from P0 to B, that angle there exceeds 90 degrees. Remember, the dot product of two vectors will be between 0 and 1 if it's within 90 degrees, if the vectors are within 90 degrees of each other, and between 0 and negative 1 if the vectors are greater than 90 degrees apart. So what I want is, if I have, let me go A. So if I have A minus P0 dot product with the normal, if that is less than 0, then that point A is behind the plane. So we'll do the same thing as before. We'll split up the dot product. We'll say A dot normal minus P0 dot n has to be less than 0. Now if we take A dot normal, component wise, that's the the normal x component times the x component of our point plus the normal y component times the y component of our point plus the normal z component times the z component of our point, and then plus, remember this negative p naught n was defined as the d of our plane, and in addition to that, this ny, nz, and x, these are actually the a, b, c, d coefficients of our plane. So a, b, c, d. So there we have it. This is actually very similar to the plane equation. So we plug this in, and if this quantity is less than 0, then the angle between the normal and direction is bigger than 90 degrees, and that point is sitting behind the plane, just like the point B is right now. And now we're almost done with the plane stuff, but the last thing I need to know is how do I get the intersection point between two points, like an edge and a plane. So imagine we have A and B here, and I want to trace it through and find this point C. So I'll just write this. I'll write that the point C is equal to the starting position A plus some scalar parameter t times the direction vector from A to B. So that is the point at B minus the point at A. In addition to that, our plane was also defined with a starting point, and this has to be orthogonal. So this point C has to be in the plane, and the direction vector from P0 to C has to be orthogonal with the normal. So what we've got is C minus P0 dot with the normal is 0. So I'll split this out. We'll have C minus, C dot with the normal minus P0 dot with the normal is 0. Now we know that this quantity is d, so if we were to bring this over, we have, well, there's a little more work to this, right? Because we have that C is equal to A plus T B minus A. But then we can say, well, this is the D of the plane. Okay, and then we will just start expanding this even further. So we have A dot with N plus T times B dot with, actually, T times B take A dot N. Then I just need to rearrange and solve for T. So first of all, I'll just write T dot with B minus A. It's times. This is a scalar. Then on the other side, I have minus A dot N minus D. And then divide by that. And then to put this back into the plane form, this is a little messy, but we have that the normal is ABC. So we have minus A, a little bit messy there, but I do what I can. And then divide by the x component of the normal, which is A. Something like that. Now what I'm going to do, I could take this value for t and sub it back in to get an expression for c, but when I go in and code this, I'm going to just return the parameter t because I want to use that as an interpolation coefficient so that I can interpolate other attributes later on. But anyway, those are the three major plane things I wanted to look at. That is making a plane, testing if a point lies behind or in front of a plane, and getting the scalar factor to indicate the intersection point between an edge and a plane. All right, let's get into the code and get this stuff done. All right, so here we are back in our project. Let's head over to our header, linear algebras, and we'll define a plane. It's pretty straightforward. All we need are the coefficients A, B, C, and D. And there we have it. That's our plane. So now I'm going to have a few things. I'm going to have a function to make a plane. So this will return a plane, linalg make plane. And what we'll do is we'll take in a 3D vector called P0 and a 3D vector for the normal. Okay, going to write two more functions. We'll have a test, so we'll have Boolean point behind plane. Now we'll take the vector that we're going to test and the plane P that we're going to test it against. And then finally we'll get the intersection. So we'll go float. Okay, so we'll take a point A, B, and the plane P that we're going to test it against. Okay, then finally we can finish off this function here. I'll just open this up. For our boundary, we're going to test this against some plane. So I'll just take these and go back to the source. Okay, so now we can get the intersection point. Just double checking. Okay, so I'll say get the parameter t. So the intersection between A and B, checking against that plane. And then I'm going to use the SIMD AVX2 operations, because the vector component is a 128-bit wide variable, so we can operate on all four components of that at the same time. So I'm going to get this by using a fused multiply and add operation with packed scalars. So what this will do is this will take the first argument times the second argument plus the third argument. So for the first argument, I'll take the parameter. So I'll say set1. So this will be setting 4 floats all to the same t value, and then I'll multiply that by b minus a. So I'll get that by the subtraction operation, subtract packed scalar. I'm going to take b's vector minus a's vector, and then to that I'm going to add a's vector. So again, all this is doing is it's doing t times b minus a plus a, just like we were doing in theory. The only difference is here we're operating on all 4 floats at once. Okay, because why not? So that has set up C to be the intersection point between these. So now we can test if B is inside. So we can go testing B against the plane. Okay, and then we'll do a similar thing down here. We want to check if A is visible. Okay, cool. So that's how we're going to use the functions. Let's go ahead and write them. So I'll just close this down and I'll go up. Let's start with making the plane. First thing I'm going to do is I'm just going to normalize this vector that I'm getting. So for A, B, and C, they will be the components of the normal. And then for D, that will be the negative of the dot product. And it's the dot product of P naught and the normal. So there we have it. Let's just return that plane. Okay, yeah, very nice. Now to check if a point is behind a plane. All we need to do is return the following expression, just as per the paperwork before. There we have it. Very nice expression. And then finally, the intersection point. So this is going to be a little messy just because I'm doing this as a compact one-liner. Remember, our goal is just to return the parameter t. If you remember, that was... So that's our numerator. And then for our denominator, we'll have the following. There we have it. So yeah, a little messy, but again, as you can see, we're taking really the dot product of the A point with the plane's parameters. We're adding on that PD. And then the denominator is the dot product of the plane's normal with the direction vector from A to B. Okay, excellent. So then the question is, how do we clip things? Well, essentially view Frustums. So we want a whole set of planes to describe the viewable region. So let's head back to the paper and have a look at that. All right, so we're almost done. We just need to somehow describe a view frustum. A view frustum is pretty much like a pyramid with the top chopped off. So imagine we have a camera and we're looking at something. The camera will have a near plane where nothing closer than this will be drawn. And as we go out from the camera, that field of view will widen out to make a far plane. And then we have the four boundaries of the plane. So remember that to define a plane, we need a point and a normal. For the near plane, the point would just be the origin. The origin at a distance, a certain distance in the z. And then the normal will be pointing away. For the far plane, the point would be at the origin, at the far distance, and the normal would be pointing back towards the camera. Then in the y, things get a little more complicated. So what we can do is we can take x equals 0, but then calculate the y coordinate for the top of the screen in world space, take that as our normal, our point, and then our normal will be downwards like that. And similarly, for the bottom, we'll get the bottom of the screen, and our normal will be pointing up. And for the right, we'll be pointing this way. For the left, we'll be pointing this way. Okay. Okay, so, all right, fair enough. But what does this actually look like? Well, remember that when we define the projection matrix, we had a few things. We had the field of view angle, which we'll call theta, and the aspect, which was the width over the height of the screen, as well as, I guess, we had the near and the far distance. Okay, so if we were to look in the y-axis, so up and down, this is y, and then here we have z. We're going with the convention where negative z is out front of the camera, the standard OpenGL convention. Imagine the camera is here at the origin, and this is our near plane, and this is our far plane. Now, trace out like this. All of this together is the full field of view angle. Half of that is the height radius, if that makes sense. So in order to calculate this point here, we'll say the top value for y will be the absolute value of the near distance. This is just to account for whether near is positive or negative. We'll just go with the absolute, times the slope of this line. Now the slope of this line is just the tangent of half the angle. I'm going with the convention where tan of an angle gives the gradient, gives the slope. So there it is. Now the y bottom value is just the reverse by symmetry. And if we were, okay, well, let's look at the tangent and normal. Okay, so as we go along, here our y, or z, our x, nothing's happening to it. Our y is increasing, and it's increasing in a certain proportion. It's increasing by y top for every, for every near step, if that makes sense. Because here we're taking a step of negative, let's say negative 0.1, for instance, and then this will be increasing by this amount for that step of negative 0.1. And so to get the normal, we simply need a vector which is orthogonal to this. The dot product will be 0. Okay, scratch all of that. All right, so back to it. All right, so I was just lost in thought for a moment. So the basic idea is if we look at this line, as this line steps across in the z-axis by this near amount, y will increase by this amount. And so the normal, we need to make sure there's a -1 here because we want it to be pointing away from us. But otherwise we just need any vector which is orthogonal. And so I'll go with near over y top, because if we multiply these together, this component becomes just positive near, and then this component becomes negative near, and then the dot product is 0. And likewise, here we have 0, and as we increase yeah, as we increase near, this is, well, it's going to decrease by y top. And so the normal here will be 0, negative near over y top, negative 1. So then again, bringing this together, we have, everything cancels out. We have positive near here, and then we have negative near here, and that cancels out to 0. So there we go. Now in the x, we have our z, and we're spreading out like this between our near and our far. So all we need to do to get the right component is take the top component, which we know will be positive, and multiply it by that aspect ratio, because that aspect ratio is a scale factor which will convert a height into a width. So what I should expect is that this plane will be 0.1 away from me. It'll be about 0.5 either way and a little bit less. So 0.05 either way, a little bit less, 0.04 on the top and bottom, or something like that. So then we have x left is the negative of x right. And then if we look at the tangents and the normal, so I'll just do the right tangent, and then the left tangent will be the reverse of that. So for the right tangent, as we step near units out, our x will increase by that x right amount. And so the tangent to that is near over x right, because then when we take the dot product, we have negative near, 0, and positive near. Yeah, okay, cool. So a little bit fiddly, and we may end up adjusting this a little bit more in the code, but yeah, let's go on and have a look at it. All right, so here we are back in our project, and yeah, we're almost done. Almost. Let's head back to the linear algebra's header right up the top here, and we'll define a frustum. So a frustum is really going to have 6 planes: the near, far, top, bottom, left, and right planes. Each of these we're going to have to clip against. So let's make a function to construct a frustum. So we're going to need the field of view y angle, the aspect ratio, the near and far, and yeah, that's it. Then finally up here, I'm going to make a function which returns, it basically does the frustum clipping. I'm going to call this linalg. Now the reason I'm calling this simple is that we're still rendering wireframes. We're not interpolating any attributes. So I'll just keep this version for now. Right, so let's jump in and make the frustum. So just pop over. Okay, so I'm just going to calculate a few parameters which will be useful. Those are the y top and x right parameters. I'll do this by getting the absolute value of the near distance times the tangent of field of view angle, half of that. Okay, and then the right coordinate will be basically the top coordinate times the aspect ratio. Okay, cool. So now we need to construct 6 planes. We'll construct the near plane. Now, like I said, I want to be at the origin, so 0 in the x, 0 in the y, but my z distance will be z of negative 0.1. It's really important to remember that these things, they're real coordinates in the world, if that makes sense. Okay, so for the normal direction, we want the near plane to be pointing away from us. Okay, now for the far plane, it's pretty much the reverse. So we're at the far, and the far plane is going to be pointing back at the camera, so we'll have the 1 there. There we go. All right, so now we need the top and the bottom. Okay, so for the top plane, our distance is still at the near distance because this is a point on the near plane. We'll just set the y coordinate to y top, and then for the normal, we'll have near over y top. And then for the bottom, we'll just reverse this. So we'll be at negative y top because we're at the bottom of the screen, and we'll reverse the direction of the normal. And that should be fine. Okay, now we just need to make the left and the right. Okay, so for the left, I need to be at negative x right coordinate, and yeah, negative near over. Okay, and I'll just take all of that and use that for the right plane. Okay, so provided that this has been done correctly, we will now have 6 planes. And when we clip against these 6 planes, that will be clipping out anything which is outside of our view. So let's finally make, where are we? This frustum clip. And what we'll do is we'll keep looping through. So we'll go for I. Yeah, so we'll take the ith plane, and use it for clipping. So remember that this clip will free the memory which has been taken up by the input. So fingers crossed we won't have any memory leaks. All right, so let's go back to our app, and things are finally coming together. So where was I? Here I make my perspective. I'm also going to make my view frustum. Okay, now I just pass in my field of view y angle. My aspect won't change, but I am going to need to flip around these near and far parameters. The projection expects them to be positive, but in world space they're negative, so we'll just put that in. Okay, so I'm just going to go down to the back face culling, and I'll get to this in a second, but back face culling isn't quite going to work right now. So I'll leave that. Now, okay, so at this point we've got our set of edges. What I'm going to do is say, okay, clip them. So I'll go lin-alg frustum clip, pass in edges, and then put in our view frustum. That should perform the clipping that we need to do, and then just down here, after we draw everything, I'll just free the edges, free the vertices. Okay. All right. So what I'm going to do is I'm just going to get this working, and then I'm going to revisit that that back face culling. So, well, the first test is, does it work? Let me just check. Yep, we're doing the clipping test. Okay, let's give that a go. I'm fully expecting errors. All right, so if we run this right now, it will look a little weird, and the reason for that is I forgot to do the perspective projection. So let's go ahead and do that now. We'll just extract point A. Yep, we'll extract point A, hit it with the projection transform, and then we'll perform perspective division. Okay, and we'll do the same thing with the y coordinate. And then we'll do the same thing with point B. And then another point, just a second ago I had a constant value 4 here, but now that we're clipping things, it's possible to clip a polygon down to 3 points, for instance. Where was I? Okay, now I'll transform these into screen coordinates. Okay, so fingers crossed, let's give this a go, see how it looks. There we have it. Okay, that's fine. What about if we push this off the side? So let's just close this down. That's all well and good. Go up to this translate, and I'm going to translate this 3 units to the left. So it should be partially off screen. And this will be the real test. This is the part I haven't tested yet. Nice. Okay, as we can see, when the polygon is partially off screen, it's being correctly clipped. So later on, when we have color attributes as well, we can be interpolating those properly. Let's just finish off these tests. Let's clip it all the way to the right. There we go. That's very nice. So when I was developing this, one of the mistakes that I made is I would do 1 or 2 tests, and then I would say, well, I guess we're done. But it's important to do a whole bunch of tests. So send it to the bottom, or the top, in fact. Yep, that's working fine. Have I messed something up here? Yeah, I should be subtracting for the y, shouldn't I? Okay. Now it should be on the bottom. Okay, very nice. Good. And then I'll just do the top and check that that's working, and that'll probably be enough. There we go. Excellent. Cool. I'm happy with that. We're clipping polygons. All right, so there's one thing that I sort of deferred to later, and that was the backface testing. Now, in projected, screen divided, perspective divided coordinates, everything seems to be working. However, I found that when I did this testing in world space, it simply wasn't. This test wasn't good enough. So we'll have to go back to the drawing board. Imagine we have really what we want is we want the direction vector from the point to the viewer to be on the same face, within 90 degrees of the normal. So what I'll do is I'll just make a new vec3, and I'll call this fragment to viewer. So this will be what is it? The viewer's position minus the fragment's position. And for the fragment, we can use any point at all. I'm just going to go with vertex A. So really the viewer's at the origin. So that is negative, because we have 0 minus each of the coordinates. Yep, there we have it. And now what I want, well, if the direction vector from the fragment to the viewer is in the same direction as the normal, then the dot product will be positive. So what I want is I want to check if the dot product is less than 0. So in other words, say the normal is pointing this direction towards me, but the direction from the fragment to the viewer is the other direction. I'm rambling, but let's test this. There we have it. So now we see we have the clipping, and the backface culling is now working correctly. Excellent. I'm happy with that. And there we have it. We are finally done with correctly clipped backface culled polygons. That's very cool. Very cool. In the next video, we'll look at filling in the polygons, getting them solid colored faces and things. But just a quick note, I don't want this to come across like this sort of stuff is really easy. Okay, if you're looking at these videos and it's taking you a while to wrap your head around planes or frustums or how they're made, that's completely natural. I am condensing a lot of work into a short little YouTube video. Do you know what I mean? It took me probably 2 days, like a full 2 days to work this out. And a lot of that was just debugging, and it was an absolute nightmare. In my original version of this code, I would print a lot of data out to the screen. So for better or for worse, all I'm saying is I've condensed this a lot, and I don't want you to feel bad if it seems a little weird, a little over your head. Anyway, hopefully it is making sense. And yeah. Anyway, so that'll be it for now. Happy coding, and I'll see you again soon. Bye.